This video focuses on a particular algorithm for solving the linear programming problem, the simplex algorithm. In the previous video, we covered basic concepts and approaches to understanding and to solving the linear programming problem. And here we turn these general concepts and approaches into the specifics of the most commonly used algorithm for most commonly used algorithm for linear programming, the simplex algorithm. You need to have understood that previous video to be able to understand this one. In that video, we talked about taking a general linear programming problem and converting it to standard form. And here we will assume that that standard form is the starting point. Remember that we have a problem where there are n optimization variables and m constraints. Each constraint forms a face of a hyperpolyhedron, and the collection of them forms a convex region. We see an example of this in the figure on this slide in 3D. For each one of these constraints, there is an associated slack variable, we have said. And when that slack variable is 0, we're at the constraint extreme. That is to say, we're on one of the faces of this constraint hyperpolyhedron. In the diagram, let's assume that the constraint in question is the one with the big polygon facing us in the diagram. Strictly, there are 6 edges of this polygon, and let us consider that we're at a vertex of that polygon, and indeed a vertex of the whole hyperpolyhedron. That is the lower left vertex of this hexagonal region, this hexagonal polygon. And the idea then of the algorithm was to move from this vertex in the up direction, assuming this polyhedron is oriented so that up corresponds to the fastest direction of fastest increase of the optimization function, and we want to move up. And we do that by releasing one of the constraint extremes, namely the one corresponding to the bottom of that hexagon, and move up towards the next vertex. And when we come to that new vertex, we have achieved a different constraint extreme. That is to say, the corresponding slack variable has become 0. And we thereby get to that next vertex. So we're talking about moving along an edge. Once we get to the end, the place where we're blocked by the new constraint becoming 0, the new slack variable becoming 0, we have to choose a new edge. And thus, in the first step, we had one constraint variable that was increasing from 0, while another one was decreasing to 0. And the same thing happens in this next step. We now choose another edge, which will correspond to one constraint variable, which will be decreased from 0. Will be increased from 0, and another one which will be decreased until it becomes 0. Initially, we've had in mind that there were m slack variables and n basic optimization variables. But now we notice that the constraints on the basic variables are that they're each one of them necessarily greater than or equal to 0. And likewise, for the slack variables associated with the constraints, they have to be greater than or equal to 0. That is, in fact, every one of the n plus m variables could be considered to be like a slack variable. That is to say, all these variables have the same type of constraints. Moreover, even the basic variables provide polyhedral faces. So we have this flexibility of considering any of the variables as the optimization variables, if you will, and any n of them, and any m be the slack variables, the ones corresponding to and the extreme of some constraint. So what happens when we're moving along an edge? Where we start at a vertex of a polyhedron or hyperpolyhedron in n space is a point at which there are n variables that are 0. N's constraints, extreme constraints. Each constraint lowers the dimension by 1 down to 0, which gives us the point that is the vertex. Whichever n variables we choose to be equal to 0, we'll call these variables the basic variables associated with that vertex. The objective function is written in terms of these basic variables. That is to say, it's a linear combination of the basic variables, weighted sum of the basic variables. And the constraints, likewise, are written in terms of the basic variables. Initially, we can say that the basic variables are the n optimization variables. But even that, we'll see later, will not necessarily be the initialization we want. The point is that at any point, we can choose the n variables that we want to be 0, and the other m are the constraint variables. Well, not strictly choose, we are at a particular vertex associated with a particular set of n basic variables. Now, an edge from that vertex, any edge, is a line, and that involves n minus 1 variables that are 0 and remain 0 as we walk along the edge. That is to say, for any one of the points on that edge, there are n minus 1 variables that are 0. There's one additional variable that starts out at 0, but we increase as we walk along the edge. And we call this the leaving variable. It leaves the basic set. The basics variables are all 0. This one becomes greater than 0, and so it leaves the basic set. So at the vertex, we have the leaving variable and then the remaining n minus 1 variables that are 0 and will stay 0. When we are at the initial vertex, the starting vertex, the vertex we've been talking about, there is this additional variable that which is going to block our way, is going to provide the constraint for us to stop this edge. That is to say, it's going to become 0 at the end of this hyperpolygon edge. That this variable will start out to be greater than 0 and will be decreased until it becomes 0, thus meeting the constraint extreme. And at that point, the n minus 1 variables that remain 0 and this new one are all 0, and thus this new variable is called the entering variable. It joins the basic set. That is to say, the set of n variables that are 0 at the new vertex. So what we've said is that all variables act like slack variables. We have n plus m of them, and any of them can be among the n plus 1 variables in question, namely the leaving variable, the n minus 1 variables that remain 0, and the entering variable. At any stage of the process when we're at any vertex, the beginning vertex or the end vertex, there are n basic variables, all of which have the value 0, and there are m non-basic variables, all of which satisfy the constraint but are not constraint extreme. And thus, identifying an edge to traverse can be restated as identifying a leaving variable from among the basic variables. That variable will change its status from basic to non-basic, and finding what the associated entering variable is that will change its status from non-basic to basic. Remember that the non-basic variables are acting as constraints. Let's call the non-basic variables x sub q. There are m of them. And they're related to the basic variables as a linear combination of them. In the initial formulation, we had a constraint equation that could be written as x sub q equals 0, greater than or equal to 0, but in the extreme equals 0. And we could write x sub q as some constant b sub q minus a sum of coefficients times each of the optimization variables x sub I. Well, now the optimization variables are not necessarily the basic variables, but we still have a set of n basic variables x sub I, and at any point in the process we will have for each non-basic variable x sub q an equation of the form shown in terms of the basic variables. Moreover, the objective function is also a linear combination of the basic variables with coefficients c sub I. Then what we see is that the processes of the simplex method are to successively first identify an edge, which will be identifying a leaving variable and finding the associated entering variable, and then changing the status of the two variables, making the leaving variable leave the basic set and the entering variable enter the basic set. But in doing that, both the objective function and the constraint equations that you saw above have to be in terms of the new basic set and not have to become in terms of the new basic set and not in terms of the old basic set. So we have a whole bunch of new a sub qi, b sub q, and c sub I to compute that will need to be written in terms of the new basic variables. And this computation of the new values, a sub qi, b sub q, and c sub I, in terms of the old values, is what's called pivoting. So, to repeat, the simplex algorithm is an iterative method with successive steps. At each step, we're starting at a vertex and identifying a leaving variable, and given the leaving variable, identifying the associated most constraining variable, which will become the entering variable, and changing the status of the two variables via the computation called pivoting. So before the pivoting computation is done, we have the collection of c sub I, which are the objective function coefficients, and all the various a sub qi and b sub q with respect to the basic variables xi. Once we have chosen a leaving basic variable, a leaving variable from among the basic set, and that variable is x sub k, and we find, in a way we'll describe later, the associated most constraining non-basic variable, x sub j, we'll need to change the status of x sub k and x sub j. What that means is that we have to compute three kinds of things. We have to compute the coefficients of the remaining non-basic variables, which were formerly in terms of the old set of basic variables, and now need to be instead of the new set of basic variables, which differ from the old set by having removed the leaving variable and added the entering variable. Then also we have to compute the coefficients of the leaving the new non-basic variable. So we need it's acting like a constraint, and we're going to need the coefficients of that constraint in terms of the new set of basic variables. And finally, we have the objective functions c sub I values that can no longer be in terms of the leaving variable, but must be in terms of the old variables, old basic variables, except for the leaving variable, and the new entering variable. This slide shows how each one of those computations go. First, let's consider the coefficients of the leaving variable in terms of the new basic variables. This leaving variable has become non-basic, and therefore we need to write its constraint as an equation. Well, we have an equation for the entering variable, x sub k, in terms of the old basic variables, x sub I. We can solve that equation for x sub k, in terms of the old basic variables. And that's all we need. That was what our objective was. Now let's consider the coefficients of the remaining non-basic variables, x sub q. Well, we also have an equation for each remaining one of them in terms of the old basic variables, x sub I. But one of those old basic variables, x sub I, is the leaving variable. And so we need to look at the equation that we solved for in the first item for xk in terms of the old basic variables other than that basic variable. And we can take that equation and substitute it in each one of the x sub q equations for the term that was in x sub k. And we'll get whatever that coefficient is of that particular x sub I, of that coefficient of that x sub k times the coefficients in the sums in the solutions for x sub k that we provided in item 1. There'll be then a couple of terms in each one of the new basic variables x sub I, and thus we'll be able to collect terms and get the new coefficients. The coefficients of the objective function work essentially the same way. We have the solution for x sub k, we put it into the ck x sub k to get ck times the solution when we collect terms to obtain coefficients of the new objective function in terms of the new basic set. Of course, these computations are detailed and have to be made quite precise, and they are made quite precise in this algorithm shown here for pivoting, in which we're recasting the constraints and the objective function given an entering variable and a leaving variable. So now we can move on to how we optimize these n plus m variables to get an optimum objective function value. We're going to do that optimization, remember, by a set of stages where we start from one vertex, choose a leaving variable, and then figure out how it's constrained most strongly, and that's going to be the computation we need to do to find the entering variable. Remember that at any stage we have n variables in the objective function. These are the basic variables. And m completely different variables are the non-overlapping subsets, form a non-overlapping subset with the set of basic variables. And we've said that each vertex to adjacent vertex move optimizes the objective function over a single one of the basic variables. And remember, it's moving from 0 to something positive. To increase the objective function by taking one of its variables that was 0 and making it positive requires that the weight of that objective function be positive. If the weight is positive and then we're increasing, then we'll increase the objective function. If the weight were negative or 0, you would respectively be decreasing the objective function by moving along that edge. So you don't want to do that. And so we look at the objective function and find which of the coefficients are positive and choose one. It's possible to choose the largest one, but in fact any one will do. That one is now our leaving variable. Now, you may be at a vertex in which none of the basic variables has a positive coefficient. And it can be shown, we'll not prove it here, but it can be shown that in that situation, you've actually reached the global constrained maximum. And thus we have a termination condition for our stages when none of the coefficients of our present objective function in terms of the present basic variables are positive, we stop. We've now chosen a leaving variable, x sub k, whose increase from 0 will bring us along the edge and increase the objective function. And we will keep going until some of the constraining variables, that is to say the non-basic variables, decreases to become 0. This will bring us to the next vertex at that point. Let's call the non-basic variable that is most constraining, that first becomes 0 as xk increases along the edge. Let's call that variable x sub j. X sub j is one of the non-basic variables, of each of which, of course, is written in terms of the basic ones. And we've been calling those x sub q, those non-basic variables. X j is one of the q. That is to say, x sub j is one of the non-basic variables. For each x sub q, we have a constraining equation of the form bq minus some aqi xi, where the xi are the basic variables, all of which are 0 except for the one that we are now increasing, that is to say, x sub k. It's clear, therefore, that the rate of increase, the rate of decrease of any x sub q is going to be a sub qk, or if you will, it's multiplied by a sub qk is multiplied by xk, all the other ones are 0. And so as xk increases, the other variable is going to decrease by a sub qk xk to the point where that value is equal to the bq. The most constraining of these non-basic variables, therefore, is the one whose aqk is largest relative to its bq value, or equivalently such that the minus aqk, the coefficient of xk, is the most negative relative to its bq value. Thus, we can compare for all the non-basic variables this ratio of aqk to bq and find the most positive of those, the largest of those. That will be our entering variable, our most constraining variable. If by some chance none of those ratios are positive, then there is no constraint. That is to say, we can move along the edge forever, and that's an indication that this original linear programming problem has no optimum. We can increase and increase without limit. Once we know what the entering variable is, that is to say, the particular one whose constraint equation is decreasing to 0, we can solve that equation for x sub k, and that will give us the increased value of x sub k. So let us recap how the optimization works. It consists of successive moves. In each move, we're choosing an edge by choosing a basic variable, one of the variables in the objective function, that has a positive coefficient in the objective function. That will be the leaving variable. And then, given that leaving variable x sub k, we find the most constraining non-basic variable by comparing the ratios of the coefficient of x sub k to the corresponding b value among the non-basic variables constraining equations. We let that be the entering variable. Given that we now have a basic variable and now this corresponding entering variable, we are in a position to pivot. That is to say, to swap to leave make the leaving variable leave the basic group, entering variable enter the basic group, and pivot to get all the equations in terms of the new basic variables. We iterate this process, edge after edge, until the pivoted objective function has only negative coefficients, meaning there's no further increase possible. We have finished our discussion of the simplex algorithm, at least in terms of the steps, but there are a number of issues that we still have to face. The first one is whether there are any constraint-satisfying solutions at all. Is there a feasible solution? This requires a test of whether the constraining hyperpolyhedron is empty. We won't go into detail how that works, but it's a fairly straightforward calculation. The next is there an optimum? Is there a top of the polyhedron, or is it open at the top? That is to say, can you increase in an unbounded way? We've seen that the search for an entering variable will answer this question for us. We've also seen how to choose an entering variable, and that is to say, how to find an edge to traverse, and leaving variable, which is to say, how to end that particular edge, saying we're at a vertex. We've also seen how we can check the objective function that we have to decide whether we've reached the optimum and can terminate the algorithm. However, there's one additional problem that we haven't dealt with, namely how we initialize the algorithm. How do we find an initial vertex to start at? This will be discussed in a couple of slides on initialization. Remind ourselves how we choose the leaving and entering variables. Really, any basic variable with a positive coefficient will do for a leaving a variable. You could choose the one with the biggest coefficient in the objective function, and that will cause the objective function to increase the fastest. But on the other hand, its constraint might be shorter than some others, and so the rate of change will be cut off too soon. So really, any value of the leaving variable will do. We've seen that the corresponding entering variable is found by a minimization with respect to the non-basic variables constraint equations, their coefficients with respect to the with respect to the leaving variable. It may be that two variables provide equally tightest constraints. They have the same coefficients. Doesn't matter, choose one. We've seen how to terminate. Subject to the availability of the initialize simplex subroutine, here we have the simplex algorithm. Its inputs are the A coefficients and B coefficients that form the constraints, the C coefficients that form the objective function all in terms of the original optimization variables. Well, to be more precise, initialize simplex takes those in and may modify them. Capital N is the list of non-basic variables. B is the list of basic variables. And the function nu here is the objective function that the objective function value that we return as the optimum. We now come to initializing the simplex algorithm. It would be really nice if we started with all the basic variables 0. So 0, 0, 0, 0, 0. Because then the objective function would be 0. But unfortunately, we may be constrained away from 0, 0, 0, 0 by one of the constraints. And so one of the constraints might not be satisfied. And thus, we cannot start simply with the 0, 0, 0, 0, the all zeros basic variables starting point. The initialization approach then involves modifying the slack variables so that after you get them, you have a set of basic variables that zeros do satisfy the modified constraints. And then we find those, we optimize those slack variables to create a new initialization of the main simplex. And so what happens is that the initialization itself requires a running of a simplex algorithm, which is accomplished by the list of items as follows: adding a new non-basic variable, and adding minus it to each constraint, making the objective function minus x sub 0, initializing the basic variables to 0, and running a whole new application of the simplex algorithm that involves doing a final pivot, a bunch of pivots, and then if we haven't made x sub 0 non-basic, at the end we do a final pivot to make x sub 0 non-basic, and this yields an initial form of the main simplex with a starting set of variables that can be set all to 0, consistent with the constraints. And we run that new simplex. Here we see the initialized simplex algorithm spelled out as an algorithm. The details are really not important for you to learn. The main point is that a solution to a nonlinear programming problem really requires two applications of a simplex algorithm, one of which establishes the initialization, and the next one, starting from that initialization, runs the optimization of the original problem. Both of these simplex algorithms need the original objective function and the constraints. We have this wonderful algorithm, but we have not talked about how we prove that it actually achieves the optimal value of the objective function within the constraints. Notice we're here not talking about that it's optimal in the sense of performance time, but rather that it achieves it actually solves the desired optimization problem. The proof involves modifying the linear programming problem that we started with into an equivalent problem which is called its dual, and in which the maximization that we had for the main problem is now a minimization. And in that dual is formed by changing the role of the constraint constants and the objective function constants, so that the constraint constants become objective function constants in some way, and the objective function constants become constraint in some way. We're not going to cover that proof at all. You're not responsible for it. If you take the Advanced Algorithms course, Comp 750, you will see how that dual work and how the proof goes. We now attend to how fast the algorithm runs. Each vertex move can be shown, for the simplex algorithm, can be shown to be theta of the number of constraints times the number of optimization variables. That is to say, the number of non-basic variables times the number of basic variables. And that's polynomial. So each step is polynomial. But it can be that the number of pivoting steps needed is what can be non-polynomial. And so the worst case for the simplex algorithm is indeed non-polynomial. However, the method is really, for most problems, very fast indeed and better than most other algorithms. There exist guaranteed polynomial order algorithms for solving linear programming, but in common usage, they may well be slower than the simplex algorithm. As we've said, there are alternatives to the simplex algorithm, and there are whole courses on them. In our Statistics and Operations Research Department, you will find such courses. Interestingly, we may solve the problem by solving an alternative nonlinear problem. It used to be thought to be obviously the case that when we had a nonlinear problem to solve, that is, in this case, that means that the constraints are nonlinear or the objective function is nonlinear or both nonlinear in the optimization variables, that the best way to solve any nonlinear problem was to locally approximate it by a linear problem, solve that, get an approximate solution which yields a better fitting linear problem, which we then solve, and we iterate that process. That is to say, we solve the nonlinear problem by successive applications of the linear problem. But it has come to be understood in regard to this particular situation of linear programming that some of the nonlinear programming solutions are so good that it's better to sort of smooth off the objective function to make it nonlinear so that it doesn't have planes and vertices, and solve the appropriate nonlinear problem for that. But we'll not get into that. Worksheet of questions you need to answer on the simplex algorithm before we do the inverted class on that. Which will begin on the Tuesday after Thanksgiving. There are a number of exercises that we'll do in that inverted session, but in this video we will not specify them, and instead I will specify them by a separate handout on Sakai. We've thus reached the end of this video.